So last time we wrote down, we're just going to jump into it, so we're starting a few minutes late. Some systems that we wanted to find the solution to. And we did for one of them, and it turns out that that had one vector that was the solution. That's what we call the unique solution. And we're going to move on to the second and the third example to see what happens here. So this is 1.2 continued. We have this example. Okay, did anyone do this one? What was the answer in this case? Just those yellow chalk, the colored chalks, they don't erase it. They have some sort of oil in them, I think. Where the color comes from is not, it's not a nice place. It comes from somewhere dark inside. Anyway, let's do this the linear algebra way, because something's going to jump out at us. So we'd augment. That would be the first step. And what would that look like here? First row.
1, -2, 3, -2. -1, 1, -2, 3. 2, -1, 3, 1.
So that's the augmented system. Now let's solve it in much of the same way that we did last time. We're going to do a bunch of row operations to try to get this into a convenient form. It's going to be row echelon form or reduced row echelon form to try to get to the solution. As we said, many ways to skin a cat, but there are more efficient ways than others. Start by establishing the top pivot. The top leftmost pivot is going to be that guy. He's already a 1. So what's the easiest way to make that into a pivot? It already is, so you literally do nothing. So row 1 I would leave alone in the first step. But I immediately want to get a 0 here and a 0 here. Let's not waste any time on that. So how would I get a 0 in this position? I can add these two to obtain that. That's a row operation, adding a multiple of one row to the other. And so I can just add these two. So this plus this is 0. This plus this, -1. This plus this, 1. This plus this, 1. So this was...
Oh, 1, sorry.
So this was row 1 plus row 2. Okay, so that's what I did. To get a 0 here, what's the quickest way you see to do that?
2 times row 1? Oh.
You can do 2 times row 2 and add them, or you could do 2 times row 1 and then subtract 1. Either way it's valid. Those are both row operations. We can do either one. Let's say we're going to do 2 row 2 and add that to row 3. So you have 2 times this plus that, 0. 2 times this plus that, 1. 2 times this is -4 plus that, -1. 2 times this is 6. Plus that, 7. Okay. So we've established the first pivot. Now let's focus on establishing the second pivot, this guy. Easiest way to do that.
Swap rows.
You can swap rows. It's also pretty easy here to multiply through by a -1. Either or, it's not going to matter. Let's multiply through by a -1. Not that swap rows was a bad idea. That was also completely okay. So I took row 2, multiplied by -1, easy enough. And so because I want to establish this pivot, I immediately want to get a 0 here. Now I want to, of course, do that in such a way that it's easy to do and it doesn't mess up the 0 that I have from here. So I wouldn't really mess with row 1 in order to accomplish that 0. I'd probably want to use row 2 and 3 so that my zeros here get maintained. So how would I get a 0 here using rows 2 and 3?
So
Just add them. I'm going to take row 2 plus row 3. Now in doing that, add these two I get 0, add those two I get 0, add these two I get 8. Now we could make this into row echelon form by dividing through by 8, but this is already, you're kind of already seeing something here, right? There are going to be 2 pivots in the coefficient matrix, right? Because this is a row of zeros, it's on the bottom. So the coefficient matrix is already in row echelon form. So let's actually start finding the solution. So how did we find that solution? What was the process we went through?
what did you write? R2 times omega 1?
Times and minus 1. Yes, here. I multiplied by a constant. How did we find the solution? What was the idea that we used to find the solution? How did we go about it? Yeah?
Is this for the third row? Doesn't it say 0 equals 8?
That does say 0 equals 8, right? So there are 2 principles that we use. One is to understand that the rows in our matrix correspond to equations. So that was the first important conceptual principle. The next one is when we want to actually start to get solutions, we want to start back substituting, finding out what one variable is and then back substituting it from the bottom row up. So you'll start by looking at the bottom row up and trying to substitute things in. But so now as we start from row 3, we realize something curious happens. Row 3 tells us that 0x1 plus 0x2 plus 0x3 equals 8. 0 equals 8 is what this tells us. That is obviously absurd. Right? That does not make any sense. Therefore, the system has no solution. The system here has no solution. It is inconsistent. Right? Here it's hard to actually tell that from the beginning, but throw it in a matrix, you'll eventually get to a point pretty efficiently where you'll have something like this happens. Right? You end up with 0 equals something that's not 0. And this is pretty much always something that we're going to look for when we want to figure out if something has no solution. So here, if at any given time we end up with a row where there are like a bunch of zeros, and on the other side of the equation there's some other number where that number is not 0, it is impossible to solve such an equation. And once such a row is obtained, we can conclude that our system is inconsistent, meaning it does not have a solution. Right? And that will be the case if and only if in the reduced row echelon form or the row echelon form you end up with this sort of situation. Right? That's pretty much going to be the only time you can end up with an equation that you cannot solve. It will be impossible to find a solution to that equation. Right? In all other situations we can find it. So our first system, we had a unique solution. Turns out this second example, we have no solution. Because saying that this thing has a solution is the same as saying 0 equals 8. So I can't say. Which is a contradiction, so you can do a proof by contradiction. If this has a solution, then 0 equals 8, therefore it does not have a solution. There's another way you can think about it. So that was our second example. First one had one vector that solved the system. Second one, no vector that solved the system, because there is no vector that's going to make that true. Let's look at the third example. We had a third one.
Closer?
Yes?
I'm sorry, so basically when one line just says...
Yeah, if any one line has something like this, a bunch of zeros, and on the other side of the equation sign, you have some number that's not zero.
Constant.
Yeah, it'll be a
Oh,
constant. Right, it's a matrix. They'll always have constants in it. Right? In this case, it was an 8, but it could have been a 1, a half, a 0.3. It doesn't matter what it is. The important thing is it's not 0, and that's bad. Because that's used the same as saying 0 is equal to something that's not 0. Let's look at the third example. That was our third example. Let me make sure that I didn't. So your C equals minus 2, minus x1 plus x2 plus x3 plus 3 plus minus 7. Okay. Because you make one little mistake here, you can mess everything up. So I always have to double check. Okay. So let's actually solve this. Let's augment. That would be 1, minus 2, 3, minus 2, minus 1, 1, minus 2, 3, 2, minus 1, 3, minus 7. I think I can fit another one here. Let's do that. Goal, establish the first pivot. That's already a pivot by our definition, so I'm going to leave that alone. Get zeros below it immediately. I can get a 0 here by adding these two, so let me do that. Row 1 plus row 2. That would be 0, minus 1, 1, 1. Want to get a 0 here. This is very similar to the last one. I can take row 2 times row 2 and add it to row 3. That would make this a 0. 2 times this plus that, 0. 2 times this plus that, 1. 2 times this is minus 4 plus 3, minus 1. 2 times this is 6. And plus a minus 7, I get minus 1. So here my first pivot is established. Now I want to focus on the second pivot in the very next row. So I'm going to want this guy to be a pivot. We can do that by multiplying that row by -1. So first I'm going to leave this guy alone. Take row 2 times -1. So that's my pivot. I immediately want to get a 0 below him. I can obtain a 0 below that by just adding these two. So I'm going to take row 2 plus row 3. 0 plus 0 is 0. Minus 1 plus 1 is 0. 1 plus minus 1 is 0. 1 plus minus 1 is 0. Now we end up in another interesting situation. It's not as straightforward as the first example. So you look at this, and you want to start back substituting. You notice that the last row says 0 equals 0, which is not wrong, right? So that's not a contradiction. It's not wrong to say that 0 equals 0. That is actually true, right? So that doesn't make something inconsistent, right? But that's not very helpful. Otherwise, to say that 0 equals 0, that's a tautology. That's true no matter what. We want to find which vectors in particular solve this system. Okay, so here's how we get around that. There are several ways we can, but there's one way that we will consider to be the standard way to get around it. Okay? The pivots, why we like the pivots to be the leading ones is because they're the coefficients of the leading variables of equations, right? So this is an equation that talks about x1 plus a combination of the other variables. This is one that talks about x2 plus some combination of the other variables, right? So you can think of x1 and x2 being the masters of these two equations. So those are guys that we can actually solve for, right? The only guy that's not a master of his own equation is x3, you might notice. That also happens to be, if we look at these columns as the coefficients of the variables, this is the x1, x2, x3, it turns out that the guy who we cannot solve for him as the subject of the formula happens to also be the guy that does not have a pivot in his column, right? So here's what we're going to do. And I'm going to write out the steps this time about how you want to think about it, how you want to set things up, but we won't write out the steps every time. Sometimes we'll just jump to the conclusions. So here, when we end up in a situation like this, it's not inconsistent, but we just have a row of zeros, or not every column of the variable have a pivot. So what you want to do here is identify. So first of all, notice it's not inconsistent. This first thing. Well, we can't solve for all variables right away. So here's what we're going to do. 1, identify columns in A. Remember, A is our standard notation for the coefficient matrix with no pivots. Right? Obviously, that's going to be the third column. Here, that's the third column. Now what we're going to do then is, because in row 1 and row 2 I can solve for x1 and x2, x3 is the only guy I can't solve for. So what I'm going to say is that x3 could literally be anything and this equation would hold, right? No matter what I plug in for x3, it's going to be true that 0 is going to be equal to 0, right? And so what we're going to do, identify the column with no pivot and set the variable of such columns. Could be variables, columns, equal to parameters, right? Because their values can vary. So what I would do here is x1 has a pivot, x2 has a pivot, x3 does not have a pivot, so set x3 equal to t. Right? I'm going to set it equal to a parameter. x3 has no pivot. Set it equal to a parameter. And that's literally okay because it's not going to change that equation. Now we can do what we've always done and start working from the bottom row up. So now we go into row 2, and row 2 would tell us that x2 minus x3 is equal to minus 1. But what does that mean? My x3 is t. So this means my x2 is equal to t minus 1, right? Whatever value you happen to plug in for x3, my x2 is going to be 1 less than that value. Then you go to row 1 to solve for x1. Row 1 says x1 minus 2x2 plus 3x3 equals minus 2. And now I can back substitute. So this means x1 minus 2, my x2 was t minus 1, plus 3x3, my x3 was t, and that would be minus 2. And so I can say then that x1 is going to be equal to, let's see what this is going to end up being. We're going to take minus 2 times the minus 1, that gives me a plus 2, right? Take that plus 2, subtract from the other side, that will give me a minus 4. Then I would have minus 2t plus 3t, which gives me t, which then I would subtract to the other side and get minus t. So that's my x1. And so here's the vectors that solve this system. So our solution would be for x1, x2, x3 will be this vector. My x1 will be minus 4 minus t. My x2 will be minus 1 plus t. And my x3 is going to be t for any t in R. Now, later on this will be important. So whenever we get something like this, we like to separate the vectors in a bit. So we're going to separate all the vectors that have to deal with t's and all the vectors that don't have to deal with t's. So I'm going to set up a constant vector, and I'm going to set up a vector that talks about all the coefficients of the t's. So who does not have a t? The minus 4, minus 1, and 0. And who has a t? Minus 1, 1, 1. And so this will be our solution to the system. And because t can be anything in R, note there are infinitely many solutions here. So it turns out not just one vector will solve this system, an infinite number of vectors will solve this system. For every t value you plug in, those sets of numbers, that triple of numbers, will actually solve that equation that I wrote down. So I can plug in t equals 0. You'll notice that in the first equation, if you plug in minus 4 for x1, minus 1 for x2, and 0 for x3, you would actually get, all the equations will work at the same time. Or you can say t equals 1. You'll notice that if you plug in minus 5 for x1, 0 for x2, and 1 for x3, that will also solve that system of equations. Literally anything you plug in, pi. Go back to that equation, plug in pi squared, plug in 7.34, anything you plug in for t, you'll notice that that equation will be solved, the system of equations that I had before. So there's an infinite number of vectors here that will solve it. Right? We get a different vector for every t value that we can pick. As it turns out, I mean, Jhevon means a lot of stuff, but there was a point to picking these 3 examples. They actually illustrate all possible conditions. This gives us our first theorem of the semester, which we are going to prove. Or this illustrates. It's an illustration of, it's one particular illustrates theorem. Let AX equals B be any n by n system of linear equations. Where m and n are positive integers. Right? So remember, m is our what we call the number of equations, and n is the number of variables. Theorem. then there are only 3 possible situations for the solution. Some books call this the variety of solutions to a linear system. 1, the system will have no solution. 'Such a system is inconsistent. This was in our second example. It's possible that you have a system and it's impossible to find values for all the variables that will work in all equations at the same time. That was what was happening in our second example. 2, the system will have a unique solution. That means exactly 1. There will be exactly 1 vector that will solve all equations in the system at the same time. That was illustrated by our very first example, the one that we did at the end of last class. 3, the system will have an infinite number of solutions. Those are the only 3 possibilities for a linear system of equations. Meaning, if you have a linear system and you tell me these 2 vectors solve the system and no others, you made a terrible mistake. It's impossible to have 2 solutions to a linear system. Okay? You will either have none, exactly 1, or an infinite amount. You will never have anything in between. Right? You'll never have just 3 vectors that solve a linear system. Impossible. The number of solutions will be 0, 1, or infinity. And there are all sorts of consequences to that theorem that we will be taking advantage of later on in the semester, but these are the only 3 possibilities. And it turns out, this isn't linear algebra when you start to talk about this. Right? You're talking about something bigger like differential geometry or something like that. But if you start looking at powers of the variables, like look at all the squares, then you're adding possibilities here, right? Then it will be possible to have exactly 2 solutions and no more. Or if you're talking about the cubes of all the variables, then it's possible to have 3 solutions, or 2 solutions, or 1 solution, or 0. But for linear systems where the powers of all the variables is going to be 1, these are the only 3 situations you can end up in. And this first situation here is the situation that we call inconsistent. And these 2 situations are the consistent situation. So consistent means some form of solution exists. Either it has exactly 1 or infinitely many. And having no solutions means it's inconsistent. Let's prove this. Anyone has an idea of where to start? How would you start by proving this?
Do you set up an arbitrary matrix or like dot system?
Sure. So, proof. Augment the system. To get AB, and what do we do with it?
Use row reduction, or use...
Right. And find its row echelon form or reduce row echelon form. Either one will be fine. So give me an arbitrary system. I can make an augmented matrix. We know how to do that. And then I'm going to reduce this augmented matrix. Right? Now I've reduced the problem of talking about any arbitrary system, just talking about a particular kind of matrix. A kind of matrix that has all the criteria of being in reduced echelon form or row echelon form. Now what can we say about that?
Would we have to branch off into cases if we do that, or could we just,
What would the cases be?
I don't know, REF and REF? No, no, wait.
Either one would be fine
Oh,
at this point. But there are cases that we have to consider.
cases with the pivots or something.
Cases with the pivots. What happened when we had a unique solution? What was the relationship between the pivots and the matrix? Versus when we had no solution, versus when we had an infinite number of solutions.
Pivot in every column?
Okay, so a pivot in every column did what? Having a pivot for every column of A meant what?
A unique solution.
That meant a unique solution. That means I could literally solve for every variable and would literally have only one answer, right? There's no variable that would get to be arbitrary, right? Because every variable would be the master of its own equation and you could solve for it, right? What was the other situation?
Where there was two pivots and there was one where that was unknown.
Right. Or you can say more generally, if you have less pivots than there are columns in A, right? Or
You have like
If you have,
all pivots and that A equals, oh, actually no.
if you have a row of zeros in each column of A, but a non-zero in B.
right, right? That was all situations, right? So let's actually break this up. So give me a random system, I can augment it, reduce it. We have two cases here. One, the system is inconsistent, or it's not inconsistent. Why can I say that? Because P or not P is a tautology. So I can make this statement. Either the system has a solution or it doesn't. Right? We can know this happens when we end up with a row of zeros and something that's non-zero. So this situation can happen when we find the reduction, or it won't happen. Right? So either this will happen or that will happen. Okay, now let's look at this happening. There are two possibilities here. Here we have subcases. Either the number of pivots equal number of columns in A, or number of pivots would be less than number of columns in A. So I have subcases A and B, and we can deal with each of those individually. So our focus was to focus on the pivots, the guys that are leading each row, the leading ones. In 2A, we have a unique solution. We can uniquely solve for each variable. In 2B, we have infinitely many solutions, since one or more variables must be parameters. They can literally take on any value they want, and the solution will be solved. So at the end of the day, we will be inconsistent, we will have a unique solution, or we will have infinitely many this exhausts all possibilities and all cases. It turns out there are only 3 of them. End of the proof. Now that has to do with a lot. So the unique solution, these are going to be the guys, well, some subset of them are going to be the guys that give us one-to-one functions. And remember I spoke about why one-to-one functions are important. So knowing that the matrix can represent functions, then it turns out that the special kinds of functions that we care about are going to be the guys that fall into this subcase. We will ignore all other matrices depending on what we're looking for. So if I want to know if a matrix is going to form an isomorphism, I'll only look at the ones that have unique solutions. I won't look at the others. And we're going to be able to characterize these matrices otherwise. So there are 3 groups a matrix can fall into in terms of solutions, and depending on our situation, we might care about some as opposed to the other ones. And we can readily identify which situation we're in by just counting the number of pivots we have. So in theory, we know all the 3 situations, but also in practice, we know how to recognize when one of these situations happen. So you augment it, find the reducer echelon form. If you have a bunch of zeros leading to something not 0 all the way at the end, it's inconsistent. If you have a pivot in every column, you can solve for one uniquely. If you don't have a pivot in every column of A, then any variable that does not have a pivot, set them equal to a parameter. And then you can solve for the solution in terms of that parameter, or parameters. And you can get a solution that way. And you can have more than one parameter. So you don't have to write this, but I'm just showing you. So let's say you had 1, 2, 3, 4, and in your reducer echelon form, you had 2 rows of zeros. Right? So that was your x1, that was your x2, that was your x3. This system will have 2 parameters, right? So you would set your x2 equals t, your x3 equals, I don't want to say s, because we always mix it up with 5. So because both of these guys don't have pivots in their column, there's only one pivot in this entire thing, and that's in the x1 column. Both of these guys get to be pivots, and so now I can go into row 1 and solve for x1. And so my x1 would be 4 minus 2t minus 3r. And so I could write my solution as 4 minus 2t minus 3r, tr, which I'd be able to split. And being able to do this is going to be important later. Split these guys in terms of all their components. The guys that have no parameters, the guys that are attached to the coefficients of t and the coefficients of r. So this would be 4, 0, 0. This would be minus 2, 1, 0. This would be minus 3, 0, 1. And so that would be the solution. So if you had a system that reduced to this would be the answer. You still have an infinitely many, because any choices of t and r will work. Yep.
Oh, there's a question. I guess I have to do with the other one too. Like, remember that book I told you about, that David C. Lee book?
Yeah.
So then he starts off with like this stuff too. Geometrically, what is that? Is that a plane containing?
Geometrically, it depends on what dimensions you're working in. So geometrically, here's what's happening. I can show you in R2. I could also draw R3, but R3 would have several cases that I don't want to. But I can show you, illustrate in R2. So we can look at R2 where our system of equations, each equation will represent the equation of a line, right? So there's one possibility of no solution. What does that mean? It means your lines are parallel and they don't intersect. There'll be no point that are on both lines at the same time. You can also have a unique solution. This means your lines are not parallel. They intersect at exactly one point. You would not have 2 straight lines crossing each other in 2 points. It's impossible. The third situation, and this is the infinite solutions, is really when one line is a multiple of the other. So they're parallel and they pass through the same point. So you have one line lying right on top of the other. So that's when you're considering something like the line x plus y equals 1 and the line 3x plus 3y equals 3, right? They're really the same line. They just might come to you in different forms in the beginning, but when you reduce them, they reduce to the same thing. And what will happen, you'd have overlapping lines. So it turns out in R2, this is what the picture would look like. You can have this situation, that situation, or that situation, right? If they're not parallel, they'll intersect. If they are parallel, they'll either never intersect or always intersect. And in this case, literally every single point on either line is a solution. Infinite solutions here. No solution there, one solution here. In R3, the situation is similar. You'll have two planes that are hovering, but their normal vectors are exactly the same, but they pass through different points. Versus you can have one plane here and intersecting another plane there. That would be an infinite number of things.
That would be two equations.
That would be two equations. And if we have three equations,
That's this one.
you'd have this weird, you can have this weird situation that like does this. And then there's another one that cuts, it's hard to draw in R3. But the point is there'd be like literally one point that is in all three planes at the same time. R3 has more situations to consider, but it's easy to see in R2, right? That there are only three cases. So that's an important idea. And for our major theorem of the semester, the equivalence theorem, this is an idea that will be used. The fact that we know when a unique solution will happen. We can derive many consequences from that. Okay. Oh, let me define a term that we sometimes use. And it's usually used when we want to talk about a situation like this without using too many words, and it's called the rank. So this is just a term we might use. We might also use the notation rank A, that's the notation, denoted. That's just more like a word. It just allows you to talk about things. So for example, if in AX equals B, and you can talk about the matrix A, B, let's say you call that one big augmented matrix B, right? And then you can talk about and where A is and M by N. Right? So let's say we have these three situations. This is just language that allows us to talk about things a lot easier. So for example, I can say if the rank of B equals to the rank of A, what would you be able to conclude there?
Unique solution.
You'd be able to conclude a unique solution here. What about if the rank of B is less than the rank of A? Is that even possible? Could the rank of B be less than the rank of A? Could the number of pivots in this thing be less than the number of pivots in this thing?
Inconsistent.
No, that's impossible. And you can talk about the rank of B being greater than the rank of A. That leads to inconsistency. It turns out that this has the unique solution or infinite solutions. And this would just break into subcases based on n. Either it's equal to n or it's less than n. And equal to n gives you unique, less than n gives you infinite. So you might see another textbook that gives you the same proof that I gave you, but they use this language, right? So instead of saying, oh, either there's a pivot in every column or blah, 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 they can just say either the rank is this and compare it to the rank of that. All right, so it just gives you more language to use. I just want you guys to know. Because it is language that even your textbook uses. So whenever you see the word rank in the textbook, this is what it's referring to, the number of pivots. Yeah?
I don't see why the rank of A and B would ever be different, because they're made up of the same elements, or the same entries. Except for the rightmost column. Like capital A and capital B.
Yeah, I mean, when we ended up with an inconsistent system, what happened? It's when we ended up with like 1, 2, 3, 4, 0, 1, 2, 2, and we had 0, 0, 0, 1. Right? This was inconsistent. This is A. How many pivots? 2. This is B. How many pivots? 3. There were more pivots in B than there are in A. Inconsistent. Because that means A has less pivots than it can deal with, but B has more. It means there's a bunch of zeros in A that B doesn't agree with. Yeah. So they can give you the same proof in a different language. I just wanted you to be aware of the language. Anyway, let's move. Because I also want to start talking about determinants today. Am I going to get there? I think we'll get there. One other thing I want to talk about, and then we move on to determinants, chapter 2. We're going to talk about homogeneous systems. The system AX equals B is called homogeneous if the vector B is actually the 0 vector. If you want to specify if you want to say this is an m by n system, this is of course going to be the m by 1 0 vector. But it's understood that that's what it would mean if your B is 0. I.e. AX equals 0 is homogeneous. And we'll use this as standard notation. So whenever you see me just write down this in the middle of some theory that I'm talking about, I'm just referring to any homogeneous system out there. Now there's one cool thing about homogeneous systems in terms of their solutions. And what can you say about the solutions to a homogeneous system?
There's always one.
There's always one, at least, right? Homogeneous systems are always consistent. You're guaranteed to be able to find a solution. There'll either be exactly one solution or infinitely many solutions. And why is that?
0.
Because there's always going to be a 0 at the end. So you'll never end up in a situation where there are a bunch of zeros here and something that's not 0 here. It's always a 0 there, right? So there's always a 0 on the right side, so you'll never end up in the inconsistent situation. You'll always have either a pivot for every column or less pivots than there are columns, and in either case you'll have a solution. It'll be unique or there'll be infinitely many, but there will be at least one. They are always consistent. They have either exactly one solution namely, can anyone, what's one solution we're guaranteed to have?
0 for each.
The 0 for each of the variables, right? No matter what the coefficients are, if you plug in 0 for each of the variables, you will end up with a 0 vector. So they will either have exactly one solution, namely that solution, or infinitely many. And another thing in our equivalence theorem, you will be able to talk about matrices that have only one solution if they're the coefficient of a homogeneous system versus infinitely many. Turns out that one-to-one functions will only have the one solution, whereas functions that are not one-to-one, you'll be able to find infinitely many solutions. So you can look at a system of equations and know about the kind of linear transformation its coefficient variable is. And I should also mention when AX equals 0, and this is a consequence of it being a vector space, by the way, that's the other solution, but we'll talk about that later. In AX equals 0, x equals 0 is called the trivial solution. Right? That's the brain dead solution that we know is there, that we don't have to look for because we know it's there. We call it the trivial solution. And theorems in the future, I'm going to talk about trivial versus non-trivial solutions. So you should know what that means. Trivial solution just means, oh, the 0 vector works. And it's easy to see that the 0 vector works. In any such situation, we call the 0 vector the trivial solution. So for any system of linear equations, only 3 possibilities: one solution, no solution, or infinitely many. A homogeneous solution is a system of equations where it's always 0 on the right side, and these guys are always consistent. They will have exactly one solution or infinitely many, because the inconsistent case will never happen. Moving on, 2.1. We're going to talk about the determinant. I believe we spoke about this in maybe the second lecture, 0, 0 or something like that. That if we had the matrix A, which is A, B, C, D, and we took a geometric interpretation on the row vectors, that the area of that guy, we found that the area would be plus or minus this expression, AD minus BC, which turns out being this times this minus this times that. And it turns out that because that was such a nice expression, we gave this guy a name. We called it the determinant of A. We're going to explore more about what that means. We're going to define it in general. And the way we're going to do our definition, there are many ways to define the determinant, by the way. The way we're going to do our definition is going to be a constructive way. By looking at the definition, you can figure out how to find it. Not always do you have those with definitions, by the way. So our definition is going to also teach you how to find it. It's going to give you a formula to compute it. I.e., the determinant gave the signed area of the parallelogram. Formed by the row vectors. We're going to want to be able to generalize this. This was the 2 by 2 determinant because this is a 2 by 2 matrix. We're going to want to generalize this to the n by n determinant in the sense that if I have an n by n matrix and I think of all the vectors as rows in Rn, row vectors in Rn, then what formula would give me the volume of the parallelepiped formed by the row vectors? This is called the determinant. Before that, oh, by the way, in Calc 3, you had something that was called the scalar triple product, which you might remember, where if you had 3 vectors A, and there was a B, and there was a C, and if you create a plane with A and B, create a plane with B and A, create a plane with B and C, and then connected all of these guys, you ended up with what we call a parallelepiped. Parallelepiped. And you learned that to find the volume of this parallelepiped, do you guys remember what that was?
A dot B cross C.
It was A dot B cross C. But how did you end up computing that? Well, it was the magnitude of A dot B cross C. That would actually give you a scalar. The dot product gives you a scalar, which could be positive or negative, so you put the absolute values around it. But this was computed as what? It was actually a determinant, right? You put these bars here. Well, they never told you it was a determinant at the time, I don't think. And you put all these guys here. These are the components of the 3 vectors. And you did that thing to find the cross product. You did the same sort of manipulation. It was this multiplied by this times this minus that, minus this multiplied by this times this minus that times that, plus this multiplied by this times this minus that times that. Right? And that actually gave you the volume. Right? This is the 3 by 3 determinant. So for A, now I'm going to talk about a little bit about notation, then we're going to start. We're going to see somewhere else this guy shows up. Then I'll talk about how to actually compute him. For A, the determinant of A is denoted by, you just put bar A or det A, right? Which is why they had that notation for cross product back in Calc 3 of the straight bars. So also if A equals something like A, B, C, D, then if you write straight bars A, B, C, D, that means the determinant of A. Right? So determinant is a straight bar notation. You write a matrix with straight bars, you're writing a determinant, which means it's not really a matrix at all anymore, it's a scalar. It's actually a volume. Here's another place determinants show up. So they show up geometrically like that, which we've illustrated before. Here's another place they'll show up. They actually show up with systems of equations. Let's say I have a 2 by 2 system of equations. This E and F. So I'm given this system of equations. Let's actually try to solve this in general. We'll also see where a solution will not exist by doing this manipulation. But let's do the elimination method. So call this row 1, call this row 2. Okay. So what I'm going to do is, let's say I wanted to eliminate the y. What I can do is I can take row 1, multiply by d. I can take row 2, multiply by minus b. Then I can add these two guys together. Notice that that would kill the y values. And I'll be left with x values. Right? I will have AD minus BC x's equals DE minus BF. Or in other words, x would be equal to DE minus BF over AD minus BC if AD minus BC not equals 0. But what is that value? That was the determinant of my coefficient matrix. In fact, the plot thickens. The numerator is the determinant of the coefficient matrix if I replace the AC with EF. Right? It turns out that this is actually equal to, the denominator will be the determinant of A, B, C, D, and the numerator is actually the determinant of EF, BD. Right? Notice that's ED minus BF, which is what we have here. So it turns out I can talk about the solution to the x value as a ratio of determinants. Pretty interesting how that works out. Another reason why the determinant seems to be such a useful thing, especially if I'm talking about the determinant of the coefficient matrix. Here A is A, B, C, D again. But in this time, instead of imagining it as vectors in R2, I'm imagining it as the coefficient of a coefficient matrix of a 2 by 2 system. It turns out that I would be able to write my x value as a ratio of determinants where the determinant of A is in the denominator. Let's actually do the same thing for y. So let's say I wanted to solve for the y, so I wanted to eliminate the x. I can do that, I just want these two guys to be the same. So how can I eliminate the x?
Multiply the first equation by C, second equation by minus A, and add.
Yeah. Oh, what, by
First
multiply.
by C, second by minus A.
So you're going to multiply this by C, and multiply the second one by minus A.
Trying to get rid of x, right?
Yeah. Minus A here. Just to make things look nicer, let's multiply the top by minus C. The signs won't matter because we have the signed, we have the absolute value to take care of it. But it's just nicer to see it right away in the nice form. So we can do that. This is me multiplying the first equation times minus C. This is me multiplying the second equation by A. Now I can add them. The x's will die. Here you'll notice I would have AD minus BC times Y. This will give me AF minus CE. So this will mean my y is equal to AF minus CE over AD minus BC, which in fact, I can also think of this as the ratio of determinants. This is actually the determinant of A. And the top is actually the determinant I get if I replace EF with the Y value. As long as AD minus BC not equal to 0. So that further reinforces that this expression is an important expression to get a hold of. It seems important geometrically. It also seems important when we're talking about solving systems, and solving systems is super important to linear algebra. So that kind of guy, and the generalization of this guy, if we have a bigger system of equations, is something useful to obtain, right? This, by the way, is an illustration of something called Cramer's rule, which we will revisit. We'll talk more specifically about it and generalize it. So it turns out that if our determinant of A is not 0, we can actually find a unique solution to the system. That's something else. Let's move on. So I just want to show you that this guy shows up all the time. So this is why we're interested in it in the first place. Geometrically it's useful, solving systems it's useful. So let's generalize this. Now there are multitudes of ways to do this, but they all have one motivation in mind. Pretty much the geometry of the situation. So we wanted some sort of expression that in the 2 by 2 case will give you the area of a parallelogram. In the 3 by 3 case will give you the volume of the parallelepiped. In the 4 by 4 case will give you the hypervolume of the 4-dimensional parallelepiped, and so on and so forth. And the idea, you start out by doing this construction, which I'm not going to do because it's very painstaking. But you do something similar to what we did when we were figuring out the area of the parallelogram. Remember when we did this guy? What we did was we created a box around it, found the area of the box was easy, and then we subtracted off the pieces. So you'll notice when we wrote down that formula, there were a bunch of things we were adding together and there were a bunch of things we were subtracting, right? So we need to come up with a formula that gives us that permutation. It adds things that should be added, subtracts things that should be subtracted. So you can work this out for the 2 by 2 case, the 3 by 3 case, and then you can prove in general using induction that the pattern that you've achieved will work. I'm not going to do that, I'm just going to tell you what the pattern is. But that was the motivation, right? We want to generalize the idea that we saw here. And this is how it comes to us. One of many ways to define a determinant. But this is the way that's easily constructible. And it gives you an algorithm to find the determinant as well. So that's why it's nice. That's why we're using this one. You'll need some definition. So this is going to be our goal for the next class. Ends at 3. I guess until the end of class. So I'm going to tell you guys how to find a determinant and then leave you in suspense for the entire weekend until we see an example. So we want to migrate from the 2 by 2 case to the n by n case. Remember, this makes sense in the square matrix situation. And so here's what we're going to do. We're going to do some definitions first, so that when I write down the definition, it'll make sense. There are things called minors and cofactors. By n matrix. The ijth minor of A denoted Mij is the determinant of the matrix obtained by eliminating the ith row and jth column of A. So our definition is going to be somewhat recursive. So I'm going to define determinants in terms of determinants to the point where it can cascade down to the 2 by 2 determinant, which we know how to find. That's going to be the idea. So I'm going to start defining things that will allow us to do this recursion. Right? So for example, let's say A is, and this can work out in general, but I'll illustrate with like a 2 by 2. A11, A12, a 3 by 3. A13, A21, A22, A23, A31, A32, A33. So I can talk about something like, for example, M23. Right, so this is just an example. Right? What is M23? This is the determinant, which is that form, of the matrix obtained by eliminating the second row and the third column. So if I go into this matrix and I eliminate the second row and the third column, you see these numbers that are left over, A11, A12, A31, A32, that determinant is defined to be the minor 2-3, the 2/3 minor. Okay? Or if I said, what is the 2-2 minor? That's a determinant that we obtained by eliminating the second row and the second column. That would have been A11, A13, A31, A33, right, and so on. That's what it means. So I can have a large matrix, and then I'm finding determinants of smaller matrices inside of that larger matrix. We call these matrices minors. They're not old enough to drink, and they're but boy, they can do arithmetic. Okay, so that's what a minor is. Let's do a definition. The ij cofactor of A denoted, this is an uppercase C, denoted Cij, is given by Cij equals almost the same thing as Mij, but it's the guy that helps us alternate the signs. It will multiply by a -1 to the I plus j. So there are some minors that will get multiplied by a -1 and some minors that will get multiplied by a +1. And this is the algebraic way to do the things where we're adding some areas and then we're subtracting other areas. That's the cofactor is going to take care of this in the computational way. So I don't like memorizing the formulas, so there's a mnemonic for this. It's to think of a checkerboard of signs. So in some large matrix, you will always have a plus sign in the top left, and then signs will alternate afterwards. Which is why when you were doing a cross product, you subtracted the middle component for some reason they never told you. Look, this is the reason. It's because there's a geometric interpretation where they had to subtract that inner area to get to the volume. So, example, in the above, we know what M23 was. In the above, C23 would actually be the negative of this guy. And C22 would actually be the +1 times that guy. Right? Why? Because when you're looking at 2, 3, the guys in the second row and third column is this guy. By applying this checkerboard, this will be a plus, a minus, a plus, a minus. So that guy takes the minus. If I'm looking at 2, 2, the guy who's in the second row and second column, this is a plus, a minus, a plus. Right? So I know there's always a plus in the top left, and I just alternate to move to whatever location I want, and I can figure out the sign that that location will take. Okay?
Do I want to?
I think I can talk about the definition now. We're going to write it down. It's going to be confusing for like the first 10 minutes or the entire semester. But when we're doing it in practice, it'll be very easy to get a hold of. But I need to write down the definition because later on when we're proving theorems about the determinant, the mathematical definition is going to be useful, and it's going to be something that we can manipulate easily. So here's the definition. Let A n by n be a matrix right? So in words, that's what it is. Here's how we compute it. Here's how we calculate it. The determinant of A would be equal to Aij Ci1 plus Aij Ci2 plus Aij Cin for any row I in A. So I'm talking about I is representing a row of A. So I'm literally taking each row element so I is a fixed number here. And it can be any row. You have a choice. I know back in Calc 3 when you were finding a determinant, you're always, when you were finding like a cross product or something, you're always expanding along the first row. But in general, you can actually choose. Or determinant of A will be Aij C1j plus Aij C2j plus Aij C and J. For any column J in A. And J is a fixed number. You can actually write this in a contracted form. We'll do that next time. But let's actually show you an example. So you're not in total suspense. We'll have a nice example here. fixing the row here. But the column, did I alternate?
Wouldn't the rows alternate for that?
No, the rows are fixed, so I want the I to stay I. The columns are changing though.
No, this one.
So this is I1, I2, In. And here, I want to fix the columns.
So the first guy
So
was
this is 1, 2, N. Right. In other words, this guy is just, it's going to be the sum. I'm fixing the Kj, Ckj. So that's a nice compact form to write it, where K goes from 1 up to N. And the shorthand for this one is the sum. K goes from 1 up to N of Ik, Cik. Right, that's the nice contracted form, right? So we like to write down the definition in this way because it gives us a nice mathematical way to manipulate things. And we're going to prove some theorems about determinants that's going to make it very easy to see, oh yeah, that has to be true, because we're going to be able to see, oh, we can factor out common terms and blah, 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 and that'll have all sorts of consequences. But let's look at an example. We're going to find the determinant of this guy, and we'll end there. 1, 0, 0, minus 1, 3, 1, 2, 2, 1, 0, minus 2, 1, 2, 0, 0, 1. So this is a 4 by 4 matrix, and we're going to use this formula to find the determinant. Okay, so step 1. Choose any row or any column. So we call it expand along. We're talking about expanding along this row or column. Okay. So someone make a choice. Where do you want to expand?
The second column,
The second column. Why did you choose the second column?
because it has the most zeros.
It has the most zeros. And why would you choose something that has the most zeros? Because the definition says, I'm going to have a bunch of things added together. It would be nice if all these coefficients were zeros. I have to add less things. So the definition kind of tells us what might be convenient. So you'll notice that in the second column, I have 1, 2, 3 zeros. In any other row or any other column, I have equal or less zeros. So it turns out to me, the best one to expand along here would be the second column, right? Because I'm not a computer, so I have to do what's easiest, right? A computer would just always do along something. You can program it, unless you're dealing with very good matrices, right? So you can choose any row or column, it does not matter. It doesn't have to be the first row. Then you apply the checkerboard of signs. And you always find it the same way. You know that it's a plus at the top left, and then you alternate. So this will take a minus sign, a plus sign, a minus sign, plus sign. So I want to populate all the signs along that column because we're going to use that column, and the signs have to be in front of them. Step 3 is now essentially follow the formula. Which I understand it might be confusing, but once you see me actually do it, it'll be very intuitive for how you should do it. So what we're going to do here is that the determinant of A, and we're doing along second column, is going to be, right? Now the A's represent the entries in the column. The C's represent the cofactors of those entries, right? So here's an entry, 0. So I'm going to take 0 times the cofactor, right? The cofactor is going to take me a negative sign. And what is the cofactor? It's when you block out everything in that row and that column. So if I block out everything in that row and that column, that's going to be 3, 2, 2, 1 minus 2, 1, 2, 0, 1. I'm writing it out, but it's not going to matter because I'm multiplying it by 0. Then I'm going to have a plus 1 times, block out everyone in his row and his column. I'm going to have the 1, 0, minus 1, 3, 1, minus 2, 1, and 2, 0. Minus 0 times, I mean now this guy, block out everyone in his row and his column. I would have 1, 0, minus 1, 3, 2, 2, 2, 0, 1. Plus 0, now I'm at this guy, times, block out everyone in his row and his column, multiply by that determinant. 1, 0, minus 1, 3, 2, 2, 1 minus 2, 1. Now notice these guys are all multiplied by 0, so they don't matter. So I broke down finding this 4 by 4 determinant to finding a 3 by 3 determinant. And we're going to repeat the process. It's going to be recursive. Now I'm going to be able to break down this 3 by 3 into a bunch of 2 by 2s, and 2 by 2s I have a formula for them, the AD minus BC. So that is equal to, now I have the plus 1 times, now we're going to do the same thing. Choose a row or column to expand along.
Second column.
I'd again choose a second because there are 2 zeros there. Here's a plus, a minus, a plus. The zeros I can ignore, so I just will have a minus 2 times. Block out everyone in his row and his column. I'll have 1 minus 1, 2, 1. And I'd have a plus 0, which I don't care about. This guy, I know how to find it. Right, this is 1 times 1 minus this times this, minus 1 times 2. And so ultimately that ends up with being 1 plus 2, that's 3 times minus 2, it ends up being minus 6. Would be the determinant. So notice what happens. You're given a matrix, in this case it was a 4 by 4. You can use that formula to break it down to a bunch of 3 by 3s. Using the formula again, break down the 3 by 3s to a bunch of 2 by 2s. Once you get to the 2 by 2 level, you have a nice formula AD minus BC to find them. So you can find determinants recursively. Just break it down one level at a time. And you can get to it. Now, one thing you have to remember, you can expand along any row or column you want. It doesn't have to be the top row. So because of the way the formula is set out, it's easier if you expand along where the most zeros are. Right? So given this, I would choose to expand along here, and ultimately I have to do less computations because I don't care about the other 3. Whereas if I chose something else, I might have to do 4 3 by 3s. So we'll stop there. That's the determinant. Next time, we'll talk about ways to create zeros if you don't have them in the first place, and how you can legally do that and not change the answer, as well as some other determinant theorems and consequences. So we'll stop there for now, and I'll see you next week. I'll also post some homework about systems of equations, maybe 1 or 2 pounds about determinants to do this weekend. So look out for that.